थिंक हाँ हो गया
रिकॉर्डिंग ऑन कर दिया है?
हाँ चलो बढ़िया अच्छा आपने नीचे ही गया था This is week 11 of Upper Thermodynamics course. So this week we'll look at compressible flows, numericals on compressible flows. This and next week will be on compressible flows. So starting with, we'll first understand what are stagnation states and what is a compressible flow, when you consider a flow to be compressible, and these are the basics to start with compressible flow, and then also some numericals on normal shock. So to give you a brief idea on this before going to numericals, so in compressible flow we need a reference where we start at any point. You take a reference and then compare. So here in the compressible flow, you take your speed of sound as your reference, and then define Mach number based on sound. So at what speed you are compared to in the flow field, at what speed the flow is compared to the speed of sound. Though the speed of sound may vary across the condition or across the flow, the condition of the flow also varies. So you say compressible when you are close to the speed of sound, or generally if you are more than Mach number of 0.3, you are called it's a compressible flow, where the compressibility effect is more. So you are compressing and the density change in the density is more. So that is a compressible flow. And what is this Mach number? So Mach number is your velocity of the flow divided by your speed of sound. So that is your Mach number. And when this Mach number is lower than 1, you call this as subsonic flow. And when it is equal to 1, whether that your flow is equal to your speed of sound, in that case you call it a sonic velocity or sonic flow. And then if it is greater than 1, your speed is greater than the speed of sound, in that case it becomes a supersonic. So you have subsonic, sonic and supersonic conditions defined based on your Mach number. And then stagnation states. So what is a stagnation state? So if in a flow you are the flow is at certain velocity, and then it has some energy in terms you're representing in terms of enthalpy. So you have, if you write a steady flow energy equation, you have enthalpy and then potential energy and kinetic energy. So potential energy, you're neglecting there is no change in height, and then your potential energy can be neglected, but you have velocity and you cannot neglect the velocity in this case. So you have enthalpy and velocity. Now if you isentropically bring this to a state where velocity is 0, then the energy processed or the enthalpy processed is your stagnation, or the properties at this point is called as stagnation properties. So you isentropically bring this flow to a stop, and the properties at this condition is called your stagnation property, and a temperature and pressure. So where do you come across this? So if you want to measure temperature or pressure, so if you want to measure temperature, there is a flow happening. You put your thermometer or the temperature measurement device, and the flow comes and hits, and the point of contact with this, so the flow is happening, but near the temperature, if you see, the fluid is at rest. So you basically measuring your stagnation temperature. So this in measurement point of view, it can create errors based on you have to take into account these effects, and but in general we assume when you're bringing this velocity isentropically to a state of rest, or velocity of 0, you call those properties as stagnation properties. And then you have normal shock. So any compressor flow or flow to a nozzle, or you assume that it is an isentropic compression process. But in case of a normal shock, what happens is your entropy will increase. It's not an isentropic process, so you will have change in property. So if there is a shock happening, so there will be a and this will happen mostly for a supersonic condition. This will happen for a supersonic condition. So, and because there you will create an entropy increase, and through a normal shock, you will have, it is called normal because it is perpendicular to your flow direction, and that's why it's called a normal shock. And with normal shock, there will be an entropy increase, and your supersonic flow gets converted to a sonic flow. So that's what happens in a normal shock, and we'll see some problems on this. So your velocity in this case is will be reduced, and so since velocity is reducing, your pressure will increase and your temperature also increase. So this all happens when a flow across a normal shock. So those we'll see, or some problems on those. So with that, we'll start some problems. The first one is, we have a stationary thermometer measures 80 degrees Celsius in an airflow that has a velocity of 200 meters per second. What is the actual flow temperature? So saying we have a stationary thermometer which is measuring 80 degrees Celsius in an airflow that has a velocity of 200 meters per second. So what is the actual flow temperature? So this is what I gave an example. So the numericals is also on those. So you have a flow, and you put a thermometer there, and this thermometer is reading 80 degrees Celsius. And what you know is the flow velocity is 200 meters per second. Since the thermometer is in contact with this flow, it will measure the whatever the fluid is in contact with the temperature thermometer bulb, that is stationary. So that fluid has come to rest. So it will measure those temperature. So whatever is given 80 degrees Celsius is your stagnation temperature. So what has been asked is to find out the actual flow temperature. So how will you solve this? So we assume that the thermometer measures the stagnation temperature, that is the probe, which can be of any temperature measuring device. It can be a bulb of a mercury or other kind of thermometer. You have a thermistor or a thermocouple junction which is in stationary. So we assume that this temperature measuring device is measuring your stagnation temperature. So that's our assumption which has been made. And then if you write the steady flow energy equation for this, so initially you have flow is coming in at some velocity and has some enthalpy. So state 1 which has velocity v1 and your temperature T1 and enthalpy H1. So this is when it's flowing to in the temperature sensing device. So that has come to a stagnation point. So at this point your velocity is 0 and you have some enthalpy H0. So stagnation properties we always write in terms of H0 or T0, P0. So this all denotes your stagnation property. So if you apply this steady flow energy equation, so your potential energy is we can neglect, and so it will reduce to H0 plus your since is a stagnation point, your velocity is also 0. So H0 plus V0 square by 2, so V0 is 0, is equals to H1 plus V1 square by 2. So we know velocity, we know temperature. So assuming an ideal gas, what you can write is T1 equals T0 minus V1 square by 2 Cp. you are writing H as CPT. Then we know velocity, we know temperature, so we can find out T1. So T naught is 80 degrees Celsius minus V1 square by 2 Cp. So substituting the values here, V1 is 200, so 200 square divided by Cp is 2000, 2 into 1.004 into 1000 to convert kilojoule into joules. So this comes out to be 20, and 80 minus 20 is 60 degrees Celsius. So your actual flow temperature is 60 degrees Celsius. Since your the flow possessed 200 meters per second, so that caused your temperature we measured at 80 degrees Celsius, which was the stagnation temperature. So your temperature measurement device is measuring 80 degrees Celsius, but your actual flow temperature is 60 degrees Celsius. So that's what it says. So moving on, next question is, so steam at 1600 kilopascal, 300 degrees Celsius flows, so it has a stagnation pressure of 1800 kilopascal. Find the velocity and the stagnation temperature. So what is being given is, we know the temperature and pressure of the flow, and the stagnation pressure is also known. We need to find out the velocity of the flow and the stagnation temperature. So how will we find this? We'll see. So what do we know? What is stagnation property? As discussed earlier, stagnation property is when you are bringing the flow isentropically to rest, the fluid to rest, so velocity is 0, then that is called as a stagnation property. So what this says is, your initial condition and when it is at stagnation property, both your entropies will be same. So because we are bringing the flow to a rest or a halt to isentropically, so your entropy is a constant. So entropy at inlet at the flow condition is equal to the entropy at stagnation point. So the flow condition is, your pressure is 1600 kilopascal and 300 degrees Celsius. So for this condition, so this is steam. So from the steam table, your enthalpy will be 3034.83 kilojoule per kg. So next is, correspondingly the entropy is 6.8844 kilojoule per kg Kelvin. Next is stagnation. At stagnation, your pressure is 1800 kilopascal. So at this point, your entropy is 6.8844 kilojoule per kg Kelvin. So from the table, so at this point, corresponding to this enthalpy and entropy, your temperature is 316.5 degrees Celsius, and in your enthalpy is 3066.155 kilojoule per kg. So V1 square by 2. So writing your equation, so H1 plus V1 square by 2 equals H0 1 at state 1. So we know H naught 1 is the stagnation property and minus your enthalpy. So this difference is equal to V1 square by 2. So we can find out velocity. So V1 is root of 2 times H naught minus H1. So it comes out to be 250.3 meters per second. So next is the product of combustion of a jet engine So next question, the product of combustion of a jet engine leaves the engine with a velocity relative to the plane of 500 meters per second, a temperature of 525 degrees Celsius and a pressure of 75 kilopascal. Assuming that your compressibility index or K is 1.32, Cp is or gamma is 1.32 and Cp is 1.15. For the product, determine the stagnation pressure and temperature of the products relative to the airplane. So what we know is, we know velocity is 500 meters per second, temperature and pressure, and gamma and Cp. So we need to find out the stagnation, pressure and temperature. So as we know, H naught equals H1 plus V1 square by 2. So we know velocity. So velocity is 500 square divided by 2000 to write it in terms of kilojoules. So we get 125 kilojoule per kg is the difference between your the enthalpy at flow and the stagnation enthalpy. So T naught minus T1 is H naught by H naught minus H1 by Cp. So H naught minus H1 we have found out to be 125 and Cp is given as 1.15 kilojoule per kg. So it comes out to be 108.7 Kelvin. So since the inlet temperature is given as 525 degrees Celsius, so converting that into Kelvin, 525 plus 273.15 plus this difference is 108.7. So it comes out to be 906.8 Kelvin. So for an isentropic process, since we are making the stagnation point to be brought isentropically, so you can do it as a isentropic compression. So P naught equals P1. P naught by P1 is T naught by T1 raised to power gamma by gamma minus 1. So we know T naught and T1, and P1 is given as 75 kilopascal. So substituting the values, and gamma is given as 1.32. So substituting, we get P naught as 127 kilopascal. So next question is, steam is flowing to a nozzle with a pressure of 400 kilopascal. The stagnation pressure and temperature are measured to be 600 kilopascal and 350 degrees Celsius respectively. What are the flow velocity and temperature? So the steam is flowing through a nozzle, and its pressure and it's given as 400 kilopascal. The stagnation pressure and temperature are measured to be 600 kilopascal and 350 degrees Celsius. So we need to find out the flow velocity and temperature. So we know both stagnation property, we know pressure and temperature. So and the pressure of the flow is known. So we need to find out the actual temperature and the flow velocity. So this is similar to what we did. So it's just the other way around. So since both the condition, stagnation property and the flow condition, both condition, your entropy is same because it's an isotropic process. So entropy is same. So we will first find out entropy, and then we can find out your temperature at actual flow temperature, and using that we can find out enthalpy, and using the enthalpy we can find out the flow velocity. So from the steam table, for 600 kilopascal and 350 degrees Celsius, so 600 kilopascal will be 0.6 bar, 0.6 MPa, and 350 degrees Celsius. So for there, my enthalpy will be 3165.66 kilojoule per kg, and my stagnation entropy will be 7.5463 kilojoule per kg Kelvin. So using this we know entropy. So entropy at both conditions are same, and entropy and 400 kilopascal, we can find out the enthalpy. So interpolating at between 2 points for 400 kilopascal and entropy, my temperature T1 is 294.7 degrees Celsius, and enthalpy is 3055.9 kilojoule per kg. So I know enthalpy now, and I know for no temperature. So enthalpy will be H naught is H1 plus so H naught is H1 plus V square by 2. So we can find velocity from here. So V will be root of 2 times H naught minus H by H. So substituting the enthalpy values, I know H naught, which is 3165.66, and H is 3055.9. So substituting, the velocity will come out to be 468.5 meters per second. So next is, how large a force must be applied to a squirt gun to have a 0.1 kg per second water flow out at 20 meters per second? What pressure inside the chamber is needed? So for this, force is nothing but your change in momentum with respect to time, so dmv by dt. Here since velocity is constant, you need to find out m dot into v. So mass flow rate is given as 0.1 kg per second and velocity is 20 meters per second. So 0.1 into 20 comes out to be 2 Newton. So delta P is half rho v square. So rho taking to the other side, we get recognized specific volume. So delta P is 0.5 v square by specific volume. So we get 0.5 into v is 20 meters per second. So 20 square divided by specific volume of water 0.001. So this comes out to be 200 kilopascal. So that is the pressure inside the chamber. So next question, estimate the speed of sound for steam directly from equation and the steam table for a state of 6 megapascal for 400 degrees Celsius. Use table values at 5 and 7 megapascal at the same entropy as the wanted state. Equation is then solved by finite difference. Also find the answer for the speed of sound assuming steam is an ideal gas. So what has been given is we have to find out the speed of sound for steam directly from the equation. So how we find the speed of sound, root of gamma RT. So and then find it from the steam table for a state of 6 megapascal and 400 degrees Celsius. So we need to find out from the table using your pressure of 5 and 6, 7 using a finite difference, assuming same entropy, and find out what will be the speed of sound, and then we need to find out, compare both the answer values. So c square is nothing but dou p by dou rho. Root of c is root of dou p by dou rho, or you can write delta p by delta rho. So at 6 megapascal and 400 degrees Celsius, my entropy is 6.5407 kilojoule per kg, and we need to find out at 7 megapascal and this entropy. And 5 megapascal and entropy to estimate the pressures, and we find out pressure delta V, because we know the pressures 7 and 5. So we know delta P. We need to find out the delta P or delta rho to find out C value. So at 7 megapascal and entropy of 6.5407, my specific volume is 0.04205 meter cube per kg, and correspondingly my density will be 1 by specific volume, which is 23.777 kg per meter cube. And at 5 megapascal and entropy of 6.5407, my specific volume will be 0.05467 meter cube per kg, and again my density will be 1 by specific volume, which is 18.2909 kg per meter cube. So now I can estimate the speed of sound. So c square is delta p by delta rho. So since we are taking a finite difference, so difference in pressure divided by change in density for this pressure. So my P1 is 7 and P2 is 5. So P1 minus P2, 7000 minus 5000, writing in terms of kilopascal to keep the unit same, divided by 23.77. 7 minus 18.2909, we get 364.56 into 1000. So writing it all in terms of Pascal. So 364.56 into 1000. So we get C is 603.8 meters per second. So we can find out Cp for a temperature difference of 50 Kelvin. The enthalpy is around 400 degrees Celsius. We get Cp as 2.0652 kilojoule per kg Kelvin. So from this we can find out Cv. So Cv is Cp minus R. So for steam R is 0.4615. So we get Cv as 1.6037. So using the Cp and Cv we can find out gamma. So it is 1.288. So to calculate speed of sound, so speed of sound is root of gamma RT. So we get 1.288, which is gamma value, into your R value 0.4615 into temperature, which is 673.15. So given as 400 degrees Celsius, so plus 273.15, and R is in kilojoule, so we multiply by 1000, so we get 632.6 meters per second. So there is a difference of 30 meters per second. So the next question is, the inlet stagnation temperature and pressure at the exit stagnation pressure of air flowing through a compressor are specified. The power input to the compressor is to be determined. So I think the values are not visible. I think I'll have to change this. So if the stagnation temperature and pressures are given at the inlet and exit, so since compression process we assume it to be an isentropic process, so even in stagnation temperature entropy will remain same. So we can directly estimate the enthalpies of the inlet and the exit condition, and we can find out the work done, or if the temperatures is been given, you can directly use m dot Cp delta T. So stagnation pressure is 900, the exit stagnation pressure is 900 kilopascal and the inlet is 100 kilopascal, and my inlet temperature is also given, so which is 308 273 is 35 degrees. This is ambient temperature. So ambient temperature, so my exit temperature will be, stagnation temperature will be, so T naught by T naught 1 equals P naught 2 by P naught 1 raised to power gamma minus 1 by gamma, since both are stagnation temperature. So the isentropic process is, and being it's an isentropic process, the entropy will remain same. So we can do an isentropic compression between these two. So we get T naught 2 equals T naught 1 into P naught 2 by P naught 1 raised to power gamma minus 1 by gamma, and T naught is your ambient temperature 35, so plus 273.15, so we get 308.2 into 900 by 100 raised to power 1.4 minus 1 by 1.4, so we get 577.4 Kelvin. And since we do an energy balance across the compressor, we get work done as m dot H2 minus H1 or H2O minus H naught O1. So H naught value can be written as Cp T naught. So m dot Cp T naught 2 minus T naught 1. So we know both stagnation temperature in the inlet and exit, and Cp of air is 1.005 and mass flow rate is 0.04 kg per second. So we get work done as 10.8 kilowatt. So next question is, carbon dioxide flows through a nozzle. The inlet temperature and velocity and the exit temperature of CO2 are specified. The Mach number is to be determined at the inlet and exit of the nozzle. So this is how the process looks. So we have a nozzle, we have the inlet condition of 1200 Kelvin and 50 meters per second velocity. So we know both in temperature and velocity at the inlet, and we know the temperature at the exit, which is 400 Kelvin. We need to find out the Mach number for both inlet and exit. So at inlet, my Mach number will be, assuming an ideal gas, we will get root of gamma RT. So gamma is 1.288 into 0.1889 into 1200 multiplied by 1000 to convert R value into joules. So we get 540.3 meters per second. So that is the speed of sound at the inlet. So Mach number at the inlet will be velocity divided by the speed of sound. So velocity here is given as 50 meters per second. So 50 divided by 540.3 meters per second, which will come out to be 0.0925. Now at the exit, my temperature is 400 Kelvin. So the speed of sound at the exit will be root of gamma RT again. So gamma R will remain same, and temperature is 400 and multiplied by 1000. So we get speed of sound as 312 meters per second. And applying an energy balance steady flow energy equation for this nozzle, my potential energy will be, change will be 0. So neglecting potential energy, we get enthalpy in plus your kinetic energy V1 square by 2, H1, writing all in specific quantities. So H1 plus V1 square by 2 equals H2, which is at the exit, plus V2 square by 2. So we know inlet velocity, we know inlet enthalpy, and exit enthalpy can be found out, and we can using temperature and Cp values, and we can find out the only unknown will be velocity at the exit. So substituting here, we get H2 minus H1 plus V2 square minus V1 square by 2 equals 0, and H2 minus H1 can be written as Cp T2 minus T1. So Cp value is 0.8439 for carbon dioxide, and temperature difference is 400 minus 1200 plus V2 square minus 50 square by 2 divided by 1000 to convert into kilojoule. So we get V2 as 1163 meters per second. So we have found out the velocity at the exit of the nozzle. So now we can find out the Mach number. So Mach number will be velocity at state 2 divided by the speed of sound at state 2. So here we should be careful that the speed of sound is also changing at the inlet and exit based on the condition. Your speed of sound also changes. So we have to estimate for both inlet and exit separately for the speed of sound. So here at the exit, the speed of sound is 312 meters per second. So Mach number is V2 by C2. So velocity at the exit of the nozzle is 1163 meters per second. So divide by speed of sound 312 gives you 3.73, which is the Mach number at the exit. So next question is, air enters a converging diverging nozzle with low velocity at 2 megapascal and 100 degrees Celsius. The exit area of the nozzle is 3.5 times the throat area. What must the back pressure be to produce a normal shock at the exit plane of the nozzle? So what is given is we have a converging diverging nozzle and your velocity is low at inlet, so your pressure is 2 megapascal and 100 degrees Celsius, and they are saying the exit area is 3.5 times the nozzle area, nozzle throat area. So what should be the back pressure, that's the exit pressure, P to produce a normal shock at the exit plane of the nozzle. So for that, first we will find out the inlet stagnation pressure. So here that will be equal to your inlet pressure, because your velocity is very low, so you can neglect the velocity or the kinetic energy. So your pressure will remain same as the stagnation pressure. So P naught 1 is equals to the inlet pressure 2 megapascal, and it is also said that A by A star, which is the exit area to the throat area, is 3.5. So using the compressibility table, we find that Mach number and the pressure ratio corresponding to the area ratio are MA1 is 2.8 and P1 by P naught is 0.0368. So the pressure ratio across the shock for this value of Mach number is, which is for 2.8, from the normal shock table we get P2 by P1 is 8.98. So that's the back pressure, which is equal to the static pressure at the exit nozzle exit, must be P2 is 8.98 times P1 and P1 is 0.0368 times P naught 1. So we get 8.98 into 0.0368 P naught 1. P naught 1 is 2 megapascal, so we get 0.661 megapascal. Next is air flows through a duct. Air flows through a duct. The state of the air and its Mach number are specified. So the velocity and the stagnation pressure, temperature and density of the air to be determined. What we know is your Mach number is given as 0.8 and temperature is given as 373.2 and pressure is 200 kilopascal for air. So that is the inlet condition. So through the duct you have air which is coming in at 200 kilopascal and temperature of 373.2, so that is 100 degrees Celsius, and you have Mach number of 0.8. So we need to find out the stagnation, pressure, temperature and density for these conditions. So for that, first we need to find out the velocity first, so that we can do an energy balance. So to find that, we will find out velocity. So velocity is for speed of sound is root of gamma RT. So gamma is 1.44 air and R is 0.287, and temperature is given as 100 degrees Celsius, so 373.2, so into 1000 to convert it into joules, so we get 387.2 meters per second. So this is the speed of sound. Now we need to find out the velocity. Since we know Mach number is 0.8, so velocity will be speed of sound times Mach number. So 387.2 into 0.8 gives you 310 meters per second. So that is the velocity of the flow in the duct. Next is we need to find out the density. So initial density is P, assuming it's an ideal gas, we get P is rho RT. So rho is P by RT. We get P is 200 kilopascal divided by R is 0.287 into 373.2. So this comes out to be 1.867 kg per meter cube. Now, so the stagnation properties can be determined as, so same expression, H naught is H1 plus V1 square by 2. So that's what we write. And if you write H naught as in terms of temperature, so you get Cp T naught equals Cp T1 plus V1 square by 2. So dividing by Cp, we get T naught is T1 plus Cp. T naught is T equals T1 plus V square by 2 Cp, and V can be written in terms of Mach number. So we get Mach number into C square, Mach number square into C square. C is again root of gamma RT, and substituting that, this is how the expression will turn out to be. So we get T naught is equals T multiplied by 1 plus gamma minus 1 into Mach number square divided by 2. So this is what we get. So this is just, we are getting it from the expression H naught equals H1 plus V1 square by 2. That is the assuming your energy flow equation, having a flow and then you bring it to a stop isentropically. So that's where we get. So and then we substituted velocity in terms of Mach number and speed of sound, and speed of sound as ideal gas assumption root of gamma RT. So that's what we did, and we get this temperature. So from this T naught is we know gamma, we know Mach number, we know temperature. So 373.2 into 1 plus 0.4 into 0.8 square divided by 2, which comes out to be 421 Kelvin. So that is the stagnation temperature. And then pressure. So since we are bringing it isentropically, so we can assume it to be doing an isentropic compression. So P naught is P times T naught by T raised to power gamma by gamma minus 1. So P is 200 kilopascal, and we know T naught and T. So T naught is 421 divided by 373.2 raised to power 1.4 divided by 0.4. It comes out with 305 kilopascal. That is the stagnation pressure. Then rho naught is again same expression as your what you write for your adiabatic process. So PV raised to power gamma. So we can use that into P into specific volume, or P by rho raised to power gamma, or substitute the ideal gas expression and write it in terms of temperature and density. So this is what you get. Density R naught is rho naught is rho into T naught by T raised to power 1 by gamma minus 1. So we know T naught and T and gamma. Substituting, we get rho we have found out 1.867. So 1.867 multiplied by 421 by 373.2 raised to power 1 by 0.4. So this comes out to be 2.52 kg per meter cube. So next is a normal shock in air has upstream total pressure of 500 kilopascal, stagnation temperature of 500 Kelvin, and your Mach number of 1.4. We need to find the downstream stagnation pressure. So what is known as, we know Mach number, which is 1.4 across the normal shock. So we use a normal shock table. So using a shock table for a Mach number of 1.5, we can find out the your upstream and downstream pressure ratios. So your downstream by upstream by upstream pressure ratio is this is stagnation pressures. So So P naught y by P naught x. So x is your upstream pressure and y is your downstream pressure. And across a normal shock, your pressure will always reduce. So you are always stagnation pressure you have reduced. So that is essentially like you are losing work, or you, that is what physically you means your entropy is increasing. So you have to do some kind of loss is there, and that is reflected in terms of pressure also. Your stagnation pressure goes down, and since your Mach number is 1.4, at higher Mach number your losses will be even larger to a normal shock. So at 1.4 you are having P naught y by P naught x is 0.95819. So P naught y will be 0.95819 into the upstream pressure, which is 500. So it comes out to be 479.1 kilopascal. So in this condition, your stagnation temperature be unchanged, and you can find out that also using the table. You will get the temperature ratio as well. So next question, consider the convergent divergent nozzle of in which the diverging section acts as a supersonic nozzle. Assume that a normal shock stands in the exit plane of the nozzle. Determine the static pressure and temperature and the stagnation pressure just downstream of the nozzle, normal shock. So we know the upstream pressure and condition in the normal shock, and across the normal shock what will be the downstream pressures and the other conditions. That's what been asked. So before the normal shock, just before the normal shock, my Mach number is 2.197, my pressure is 93.9 kilopascal, my temperature is 183.2 Kelvin, and my stagnation pressure is 1000 kilopascal. So we need to find out the similar properties downstream of the normal shock. So again, I will go back to the normal shock table, and for this Mach number of 2.197, I will find from the table the downstream Mach number, and it will come out to be 0.547. So that's what we discussed at the start of the class, where what happens across the flow of nozzle. We said supersonic, it gets converted to a sonic flow, and that's what we observe here. From 2.197, the Mach number has dropped to 0.547. So Mach number less than 1 says it's a subsonic flow. So Mach number is 2.197, and a downstream Mach number is 0.547, and the pressure ratios are Py by Px is 5.46 and Ty by Tx is 1.854, and P naught by Py by P naught x is 0.63. From the table this ratios is given. So from this now I can estimate the downstream pressures. So Py is 5.46 times the upstream pressure. So 5.46 into 93.9 gives you 512.7 kilopascal. So that is the downstream pressure. Next is Ty. Ty is 1.854 times Tx, so 1.854 into 183.2, which is giving 339.7. Just see if I can find out. So for us the Mach number is 2.197. So this is how the shock table will look like. We'll have the Mach condition, Mach 1 upstream Mach number, the downstream Mach number, your pressure ratio of the downstream to upstream, then your density at downstream to upstream, and similarly temperature downstream to upstream, and your downstream stagnation pressure divided by upstream stagnation pressure, and your pressure upstream divided by your stagnation pressure downstream. So this all ratios is given in the normal shock table. And for our condition, so our condition, the Mach number was 2.197, so close to 2.2. So what we got is 0.5471 for the Mach number downstream, and then your P2 by P1 is 5.48, so that's what is given. So we got 5.46 because you have to interpolate between 2.197 and 2.2 for 2.197, and your rho 2 by rho 1 is 2.95, which is not required for us. We require P0 2 by P0 1, which is 0.6281, so we got 0.63, and then temperature downstream upstream, which is 1.8569, we got 1.854. So that's how you read from a normal shock table. Then we get Py is 5.46 times Px, so 512.7 kilopascal, and then Ty is 1.854 into upstream pressure, so 1.854 into 183.2, which gives you 339.7 Kelvin. So here you have to be careful, you have to always multiply by Kelvin, a temperature, and then P0 y is 0.63 times P0 x, which is the upstream stagnation pressure, which is 1000 kilopascal. So 0.63 into 1000 gives you 630 kilopascal. So those are the conditions downstream of the normal shock. So before going, just based on what we did, so we'll discuss how the properties are varying for a normal shock. So discuss the effect of a normal shock wave on several properties. So one, what is happening is, we saw the Mach number was supersonic and it went to subsonic condition. So what is happening is your velocity is decreasing. Then if you see, your temperature was increasing, your ratio was higher, greater than 1, so your temperature is increasing downstream. So and pressure is also increasing, so that is if your velocity is decreasing, your pressure increases. So that's what is happening here. If you see, pressure also increases, and your stagnation temperature will remain same, because your enthalpy, stagnation enthalpy will remain same. So you have same stagnation enthalpy, so your stagnation temperature will remain same, but your stagnation pressure will decrease. And then your static pressure will increase, so will decrease, and then your stagnation pressure is decreasing. So this is how it looks in a chart. So if you plot this Rayleigh line and Fano line, this crosses this 2 point here, and this A and B is your Mach number equals 1, and the bottom portion says the supersonic condition, and top gives you subsonic condition. So your flow is from this x to y through a normal shock wave. Instead of following this lines, it now crosses jumps from here x to y, so because of which you have pressure drop from P0 x, which is the static pressure, to P0 y. So your enthalpy at this two condition will remain same, and if you see, the velocity has decreased from this to this. So what is it saying is, across a normal shock you have a velocity decrease, and then your temperature will increase, and then your pressure will increase, and then your static pressure or your stagnation pressure will reduce, and your stagnation temperature will remain same because your stagnation enthalpies are same. So with that, the next question is, a flow into a normal shock in air has a total pressure of 400 kilopascal, a stagnation temperature of 600 Kelvin, and a Mach number of 1.2. So find the upstream temperature, the specific entropy generation in the shock, and the downstream velocity. So from this thing we know Mach number is 1.2. So I'll present again the shock table. So we know Mach number is 1.2. So for this condition, your T2 by T1 is 1.1280. And here T2 by T by T naught is not given. So this is your compressibility table for stagnation properties, finding out stagnation properties. And see if I can find. So here my Mach number is 1.2. So Mach number is 1.2. So correspondingly, for isentropic flow table, if you see T by T naught is 0.7764. So that's what is written here, 0.7764, and the P by P naught is 0.4124. So here from this, instead of calculating this thing, you can directly find out the stagnation property from this table. So 0.4124, and from there you can find out the stagnation pressure and stagnation temperature, and if it's known, you can find out the other way around. So we don't know the temperature, so we know the stagnation temperature is 600 Kelvin. So 0.7764 into 600 gives you 465.84. So we know the temperature, we know the pressure. So now we can find out the from the normal shock table for 1.2. We know we can find out the temperature ratio. So 1.128 and 0.4154. No, we need to find out P2 by P1. P2 by P1 1.5133. So 1.5133 and 1.128. So that's what we got from the table. And your Mach number downstream will be 0.8422. So 0.8422. So the change in entropy will be Sy minus Sx is if you calculate Cp ln T2 by T1 minus R ln P2 by P1. So we know the temperature ratio and pressure ratio between T2 by T1 and P2 by P1. So substituting the values, so we get 1.004 for air into ln 1.128 minus R is 0.287 into ln 1.5133. So we get as generated is 0.00203 kilojoule per kg Kelvin. So that is the entropy generated for flow across the normal shock. Next is from the shock relation, which we found out, the downstream pressure will be temperature will be 1.128 times the upstream temperature. So 1.128 into 465.84, which gives you 525.47. Kelvin. So now we know temperature, we can find out the velocity. So we know Mach number at the downstream condition, which is 0.84217. We need to find out the speed of sound at the downstream condition to find out the velocity. So downstream, the speed of sound is root of gamma RT. So V will be Mach number downstream into root of gamma RT. So substituting 0.84217 into root of 1.4 into R is 0.287 into T is 525.47, which we have found out, into 1000. So this gives you 387 meters per second. So your downstream speed of sound is 455.49 and the velocity is 387 meters per second. So if you see here again, you can see that the velocity has reduced and it has went to subsonic flow. So next question, steam flowing at 15 meters per second and 1800 kilopascal and 300 degrees Celsius expands to 1600 kilopascal in a converging nozzle. Find the exit velocity and area ratio, and we have to solve the problem using a stream table. So we'll say inlet state, my specific volume will be 0.14021, so at 1800 kilopascal and 300 degrees Celsius, and enthalpy will be 3029.21 kilojoule per kg, and entropy is 6.8226 kilojoule per kg Kelvin. And exit pressure, exit condition, your entropies will be remaining same for the flow, and so exit pressure will be, so we are assuming isentropic flow. So specific volume for this exit pressure and entropy 6.8226 and exit pressure of 1600 kilopascal. So we get specific volume as 0.153371 meter cube per kg and enthalpy is 3000.995 kilojoule per kg. So the energy equation will be Vi square by 2 plus Hi equals V square by 2 plus He. So V square will be Vi square plus 2 into Hi minus He. So V is root of this term. So root of velocity at the inlet is 15 meters per second. So 15 into 15 plus 2 into 1000 to convert it into joules into 3029.21 minus 3000.995, which gives you velocity at exit is 238 meters per second. So this is a simple energy balance. Next is the area ratio. So area ratio is we can do a mass balance. So mass in is mass out. Mass we can write it as rho AV. So rho into volume flow rate, and volume flow rate is area into velocity. So rho into area into velocity. Rho you can write it as specific volume, 1 by specific volume. So A exit by A inlet is velocity specific volume at exit by specific volume at inlet into velocity at inlet by velocity of exit. So we get 0.15371 into 15 divided by 0.14021 into 238, which comes out to be 0.06909. So that is the area ratio. Next, if we solve this as an ideal gas equation with constant specific heat, so which is gamma is 1.327. So for isentropic condition, Te by Ti is Pe by Pi raised to power gamma minus 1 by gamma. So we get 573.15 into 1600 divided by 1800 raised to power gamma minus 1 by gamma, which comes out to be 556.76 Kelvin. So that is the exit temperature. Now if we substitute similarly, instead of finding enthalpy from the stream table, find it from 2 Cp delta T. So this is what we get. So we know the inlet temperature 573.15, which is given 300 degrees Celsius. So in exit we have found out 556.76. So we get a velocity of 248 meters per second. So which is close. And the area ratio then will become, so V I specific volume divided into velocity. So specific volume we are writing in terms of pressure. So because P specific volume raised to power gamma is constant for an adiabatic reversible adiabatic flow, isentropic flow. So Pi by Pe raised to power 1 by gamma into velocity Vi by Ve. So substituting the values, we get area ratio as 0.0661. So previously got 0.069, here we are getting 0.066. Next is air enters a normal shock at 26 kilopascal, 230 Kelvin and 815 meters per second. Calculate the stagnation pressure and Mach number upstream of the shock, as well as pressure, temperature, velocity, Mach number and stagnation pressure downstream of the shock. Calculate the entropy change of air across the normal shock wave. So this is again similar to what we did. So initially for that we will find out the initial stagnation temperature and pressure upstream. So T01 is again T1 by V1 square by 2 Cp. So substituting the value, T1 is 230 Kelvin. So 230 plus velocity is 815 meters per second. So 815 square divided by 2 into Cp is 1.005 into 1000. So this gives you 560.5 Kelvin. Next is P naught. So P naught is P1 into T naught by T raised to power gamma by gamma minus 1. So P is 26 kilopascal, and substituting the temperature, stagnation temperature and temperature, we get P naught as 587.3 kilopascal. So the velocity and the Mach number before the shock are determined from ideal gas question, assuming ideal gas, we get speed of sound as root of gamma RT. Gamma is 1.4, R is 0.287 for air, and then T is known is 230 into 1000. To convert it into joules, we get 304 meters per second. Then the Mach number upstream will be V1 by C1, which is 815 divided by the speed of sound is 304. We get Mach number as 2.681. So going back to the shock table, for 2.681, so 2.68, we get the Mach number at our downstream is 0.4972, and then P2 by P1 is 8.218, and T2 by T1 is 2.3217. So that's how we say, and then P0 by 2 by P1, that is here P1 by P0 is 0.1028. So this is a reciprocal of that. that's what is given here. So Mach number downstream is 0.4972, and then P naught by 2 by P1 is 9.7330, and P2 by P1 is 8.2208, and T2 by T1 is 2.323. Then the stagnation pressure P naught we can calculate. So P naught is 9.733 into P1, which is 26 kilopascal. So it will come out to be 253.1 kilopascal. Then P2 is 8.2208 into P1. So 8.2208 into 26 gives 213.7 kilopascal. Then T2 is 2.323 T1. So 2.323 into 230, which is 534.3 Kelvin. So that is the temperature downstream. Now we need to find out the velocity. So velocity is again Mach number into speed of sound. So Mach number we have found out 0.4972 into speed of sound is root of gamma RT. So 0.4972 into root of 1.4 into 0.287 into temperature which we have found out 534.3. So 534.3 into 1000, so gives you 230.4 meters per second. So the entropy change across the shock is determined to be S2 minus S1 equals Cp ln T2 by T1 minus R ln P2 by P1. So T2 by T1 and P2 by P1 is already we have got from the chart or the table. So substituting the value, Cp is 1.005 and R is 0.287. Substituting the value, we get S2 minus S1 as 0.242 kilojoule per kg Kelvin. So the shock wave is creating a dissipation, and so that's what the shock wave is highly dissipative process, and this is because of the flow through the shock wave. And so if the air flowing through the converging diverging nozzle experiences a normal shock wave at the nozzle exit plane, determine the flows following after the shock: the stagnation pressure, static temperature, and the static density, the entropy change across the shock, the exit velocity, and the mass flow rate through the nozzle. Approximate the flow as steady in one dimensional and isotropic with gamma as 1.4 from the nozzle inlet to the shock location. So inlet condition is given, properties are given here. We need to find out that exit. So again, going back to the shock table, we have to find out. So P01 is 1 megapascal, P1 is 0.1278 megapascal, and T1 is 444.5 Kelvin, and Rho1 is 1.002 kg per meter cube. This all is given as from the question. So we need to find out the downstream condition. So for that, we go to the normal shock table for Mach number of 2. So this is the Mach number of 2, and we use find out P02 by P01, P2 by P1, rho T2 by T1, and rho 2 by rho 1. So this Mach number at 2.5774, P2 by P1, P0 by 2 by P0, P2 by P1 is 4.5, then rho 2 by rho 1 2.667, T2 by T1 1.6875, and P02 by P01 is 0.7209. So that's what is given here, and then we use that to find out the downstream properties. We know upstream properties, we just multiply with the constants here, and we get P02 as 0.7209 P01. So 0.7209 into 1, we get 0.721 megapascal. Then P2 is 4.5 in times P1, so 4.5 into 0.1278 megapascal. So P2 will be 0.575 megapascal. Then T2 is 1.6875 T1, so 1.6875 into 444.5 which gives you 750 Kelvin. Then rho 2 is 2.6667 rho 1, so 2.6667 into 1.002 kg per meter cube, so it gives you 2.67 kg per meter cube. So the entropy change across the shock is S2 minus S1, so Cp ln T2 by T1 minus R ln P2 by P1. So we have found out T2 by T1 and P2 by P1 from the shock table. So we get 1.005 into ln 1.6875 minus 0.287 into ln 4.5, which comes out to be 0.0942 kilojoule per kg Kelvin. So thus the entropy of the air increases as it passes through a normal shock, so which is highly irreversible. Next is we need to find out the velocity. So since we know Mach number, we can find out velocity. Mach number into root of gamma RT. So Mach number is 0.5774, root of 1.4 into 0.287 into T is 70.1 into 1000, which gives you 317 meters per second. So the mass flow rate through the converging diverging nozzle. So what will happen is the mass flow rate will not change, so the mass flow rate will remain same, and because of the shock, it is not, the mass flow rate will not change. So you have the inlet mass flow rate which is there, so will remain same. So mass flow rate is 2.868. So just the downstream conditions are changing, but your mass flow rate will still remain same, irrespective of the shock wave. So converging diverging nozzle operates at a steady state. Air as an ideal gas with gamma 1.4 enters the nozzle at 500 Kelvin, 6 bar and a Mach number of 0.3. So that is the inlet condition, 500 Kelvin, 6 bar and 0.3 Mach number. So the air flows isentropically to the exit plane where a normal shock stands. So the temperature just upstream of the shock is 380.416 Kelvin. Determine the back pressure in bar. So since normal shock is forming at the exit plane, so first we need to find out the stagnation temperature and stagnation pressure for Mach number of 0.3. So T1 by T0 is 0.98232. So from the isentropic table, Mach number of 0.3, we get T by T0 is 0.9823, and then from there we get T0 1 is 500 by 0.68965, which gives you 509 Kelvin, and then P1 by P0 is 0.93947. So P0 is 6 by 0.93947. We get 6.39 bar, which is the stagnation pressure. So since flow is isentropic through the nozzle, your stagnation temperature and stagnation pressure remains constant up to the exit plane. So T0x and T01 will remain same, and pressure will remain same. So now we need to find out the Mach number at the just upstream of the normal shock at the exit. So Tx by T0 is 380.416 and 500, so we get 0.74768. .416 divided by 500, which is 0.74768, 0.74768 is close to somewhere around a Mach number of 1.3. So that's what is given. Mach number is 1.3 from the isentropic flow table, and then for this Mach number of 1.3 we go to the normal shock table, and we find out here, that's what we get, 0.74768. So 74768 is somewhere here. So we get Mach number of 1.3, and then we go to the normal shock table 1.3, and we can find out the downstream pressures. So Px by P naught is 0.36092. So pressure will be 36.39 times 0.36092, which gives you 2.306 bar. And similarly, Py by Px is 1.805. So your Py is 2.306 into 1.805, gives you 4.162 bar. So initially your pressure was 2.306 bar, now it has increased to 4.162 bar, and this stagnation pressure will also be reduced, but your stagnation temperature will remain same here. So with this I have finished what I have prepared for today. So we have covered stagnation properties, how to calculate stagnation property, and how to calculate the compressible properties, and how to calculate the Mach numbers, and how to find one if one is known, another is unknown, and how to use the tables. And then we saw flow across some nozzle. We also calculated the velocities and so on, the forces applied, and then we went to normal shock, and we saw what is happening across the shock, and how the properties are varying, how the properties are downstream and upstream, how to calculate. So from the Mach number we went to the shock table and saw how we use the shock table to estimate the properties, and it can also be found out using the values derived, so which will be then they covered next week. So we can use the values as well, equations, to find out directly instead of going to the table. So that can also be done. So here we are I just showed you with respect to the chart how to calculate the properties for the normal shock, and this we have covered this week's content, and next week we will see some compressible flow again through nozzles and other conditions, and then that I will end the session for today. So again we will meet on next week. So that will be the final week for the applied thermodynamics course, where I will cover continuation of this compressible flow, and then I will also taking a review class on additional class on Wednesday at 5 I will be taking, and there we will go through all over the course, which was the contents which are covered in the 12 weeks. So that's all for today. Thank you.